actually here you can, if you want, you can use Jacobian method, but I also use the moment generating function form. Okay, so for the proof, so moment generating function of standard normal. So for normal PDF, the moment generating function of normal from the previous notes. So we have e to the mu t, but mu is 0, so we don't have that term, and then plus sigma square t square over 2. So our sigma square is just 1, so we will have t square over 2. Okay, so that's it, that's easy. So the range of t should be given where this function is defined, is important. Okay, so so we have moment generating function of x square t. Okay, so let's write the definition. E to the t x square. Okay, so we know so our random variable is x here. So we want to find the expectation of this function like gx. Okay, so from infinity minus infinity to infinity, e to the t x square. Okay, then the PDF of standard normal. I believe you all know this. You should know it. Okay, so this is the PDF of normal 0, 1. Okay, so let's open up the square. So from minus infinity to infinity, let's write 2 pi. Here we have e to the t x squared. We have we can combine them actually. So why didn't I combine them? I don't know. Okay, so what are the common things here? X squared terms. For the normal distribution, remember we have x squared over 2. So let's write this as a function. Why it's not writing? Let me see. Still in this eraser form. Oof, why it's always appearing? Okay, so write this as minus x squared over 2. Okay, then when we do that, we will have 1 minus, we have t over 2t. Sorry, 2t. Right? Because we make it at minus x squared over 2 parentheses. So t x squared will be minus 2t in the parentheses of that. And we have dx. Okay? Okay. Okay, so so this is actually this looks like a PDF of normal distribution. Consider, let me use a different color. Okay, so this is the PDF of standard normal, right? So we have 1 over 2 pi part here, and then instead of minus x squared over 2 term, this is multiplied by minus 1 over 2t, or we can consider it as 1 over sigma square term. Okay, so it's close to the form of the standard normal distribution, but we have to multiply it by another form. So this part is like okay, so we have 1 over 2 pi, okay, e to the minus x squared over 2 sigma square. Okay, so a regular form of the normal distribution with mean 0 and variance 1. Okay, so PDF of normal with mean 0 and variance sigma square. We don't know the sigma square yet. Actually here we know sigma square. Sigma square will be 1 over 1 minus 2t term, right? It is given like that. So we can replace it this way. But in the PDF form we have we have to add sigma square in this part actually, or sigma term. So we don't have that sigma term. So what we have to do is multiply and divide this by sigma term. What is sigma? Minus 1 over 2t actually. Okay, so then this will be, the whole thing will be a PDF of normal, and in the range of minus infinity and infinity, without taking an integral, we can see that it will be 1, or this one of the sigma terms will go out. Okay, and then what we have here, Okay, so when we write it this way, so we will have 1 over 2t and 2 pi 1 over 2t, right? And then we have e to the minus x squared over 2 1 minus 2t dt, the dx, not dt. Okay, so this will give us the form. So when we consider this part, so this part will be the exact PDF of normal with 0 mean and 1 over 1 minus 2t variance. Okay, and then with integral, actually with integrating it, this integral will be, so this part will be the PDF and the whole integral part will be 1. Okay, so what's our outcome of the integral? It is okay, I forgot the standard deviation. So this part will be the standard deviation. Sorry, I forgot to put in them in square root, or let's write 1 over 2 and 1 over 2 parts, because the variance is 1 minus 2t. So this is 1. And okay, so let's continue. Then what we have here is 1 minus 2t minus 1 over t. Okay, again the range will be the range of the t is changed as this one, because otherwise this value will be infinity. Okay, so the moment generating function of y is obtained as 1 over 2, where t is less than 1 over 2, which is the MGF of chi-square, with alpha is 1 over 2, right? Beta is 2, so multiply these two, so 2 times alpha, chi-square 1. Okay, so this is the end of the proof. Which other theorems we have related to chi-square distribution? Okay, okay, without proofs we can do these actually. Theorem. In this case we have a random sample. Using the previous theorems we can show that. So when we have a random sample of size m from normal distribution with mean, mu and variance sigma square. Okay, so this is given to us, distributed. Then, okay, when we consider zi equals xi minus mu over sigma normal 0 1. Okay, with this transformation, again you can use simply moment generating functions to show that, or any transformation rule. This is about the first theorem about the normal distribution related to linear combination of normal distributed random variables will be again normal. So you can prove it like that. And we know that when we have a standard normal distributed random variable, the square of that will be chi-square distributed with degrees of freedom 1. So using this without any proof, actually, without using the previous proofs, actually, we can say that. And then when we combine the sum, we also showed that, proved that I from 1 to n, which is summation of xi minus mu whole square divided by sigma square I from 1 to n will be chi-square distributed with n degrees of freedom. We also proved that. And from here, then x bar, which is summation of the I over n, right? Distributed as normal with mean mu sigma square over n. And from here, when we standardize normal distributed random variable, we ended up with standard normal. And from here, when we take the square of this, we will end up with chi-square with 1 degrees of freedom. Okay, so we will use these type of things a lot in the examples when we combine everything. So we will see also T and F distributions. Okay, so the sampling distribution of S squared does not follow directly above theorem. So let's okay. Let me see how many minutes that we are. Okay, so let me stop here, and then in another video I will continue with other theorems related to the normal distribution and chi-square, and then we will start seeing the sampling distribution related with the T distribution.